Hello, and welcome to this video about the first fundamental theorem of calculus. We will explore what the theorem says, how it works, and how it can be applied. But first, a little bit of background. Recall that the area under a curve can be estimated by adding a bunch of rectangles or trapezoids. The more we add, the better our estimate will be. There are various ways to do this, but no matter how many we add, this method will always produce an estimate. The general calculations look like this. Also recall that antiderivatives are sort of reverse derivatives. In other words, the antiderivative of f of x equals x squared is big F of x equals 1/3 x cubed plus c, because the derivatives of all functions of the form 1/3 x cubed plus c are x squared by way of the power rule. Likewise, the antiderivative of f of x equals cosine x is big F of x equals sine x plus c, since the derivatives of all functions sine x plus c are cosine x. Usually an indefinite integral is used to denote an antiderivative. The integral f of x dx is equal to big F of x plus c. Now for the big question, how would we find the exact area under a curve? We would use the fundamental theorem of calculus. There are two parts to this theorem. The second has its own video. And the first part says, if f of x is continuous on the closed interval ab, and if the integral of f of x dx is equal to big F of x on the closed interval ab, then the integral from a to b of f of x dx is equal to f of b minus f of a. This represents the area over the closed interval ab from the x-axis to the function curve. This is called a definite integral because of the limits of integration. A is the lower limit, or the left boundary, and b is the upper limit, or the right boundary. Here's a quick demonstration. To find the area under the curve f of x equals x squared over the closed interval -2 to 3, first set up the definite integral. Then find the antiderivative. The vertical bar indicates that the antiderivative has been found, but the final calculation has not yet been done. There are some properties to keep in mind. First, the integral from a to a of f of x dx equals big F of a minus big F of a, which equals 0. The area of a region of 0 width is 0. Second, switching the limits of integration makes the area negative. Traditionally, area is positive because it is thought of in terms of squares, both the shape and squaring numbers, which cannot be negative. In this case, since it changes the order of subtraction, the result changes signs. For example, third, a similar result happens when the function is below the x-axis. Making the function negative, we have this. From this diagram, we can make several observations. The integral from a to c of f of x dx is less than 0. The area is being calculated from left to right, and the region is below the x-axis. The integral from c to a of f of x dx is greater than 0. The area is being calculated from right to left, and the region is below the x-axis. This is the equivalent of a double negative in language. The integral from c to b of f of x dx is greater than 0. The area is being calculated from left to right, and the region is above the x-axis. The integral from b to c of f of x dx is less than 0. The area is being calculated from right to left, and the region is above the x-axis. The integral from a to b of f of x dx is greater than 0. The area is being calculated from left to right, and the region below the x-axis is smaller than the region above the x-axis. The integral from b to a of f of x dx is less than 0. The area is being calculated from right to left, and the region below the x-axis is smaller than the region above the x-axis. The integral from a to a of f of x dx is equal to the integral from b to b of f of x dx, which is equal to the integral from c to c of f of x dx, which is all equal to 0. These regions have 0 width, so they have 0 area. What does the area under the curve represent, other than a theoretical geometrical area? It could represent all kinds of things. Suppose a function d of t represents the distance in miles from home traveled over time in hours on a trip. D of 1 would tell us our miles from home after 1 hour, and d of 10 would tell us our miles from home after 10 hours. The derivative function d prime of t would tell us the rate of change of our distance from home. So d prime of 1 would tell us how fast we are going in miles per hour at 1 hour, and d prime of 10 would tell us how fast we are going at 10 hours. Thinking in the other direction, the integral from 1 to 10 of d prime of t dt gives us the total distance traveled from 1 hour to 10 hours. Something important to note is that there's a kind of hierarchy with functions, derivatives, and integrals. Let's take a look at an example. Suppose water is draining from a tank at this rate. How many gallons drain from 1 to 2 minutes? "600 gallons drain from the tank between minute 1 and minute 2. Note that we don't have enough information at this point to figure out how much water is still in the tank. To figure that out, we would need to know the initial amount or how much drained in the first minute. Here are a few practice exercises. Pause the video and give them a shot. Think you've got them? Let's take a look. Now let's take a look at our second problem. So for part A, we're going from 4 to 4 of this same expression up here. But when we go from one number to the same number, that means we're covering no distance, so it's equal to 0. For B, we have the same expression, except our limits are switched. So instead of from negative 2 to 4, we have from 4 to negative 2. So that means we're going to take this answer and make it negative. So we have negative 96. For part C, we have the same limits of integration, except our expression has been flipped over the x-axis, which all that really means is we just distributed a negative throughout the expression. So since we did that, we're going to take this answer and make it negative again, negative 96. And for our final one, we flipped our limits of integration and we flipped it over the x-axis, so we distributed the negative again. So we're going to have our answer similar to part B, except we're going to change the sign of this one, so it's going to be positive 96. Let's try one more. A particle moves along a straight line and has velocity function p of t equals negative 3t squared plus 24t minus 14. How many meters does it travel from t equals 0 to t equals 3 seconds? If you want to try this one on your own, pause the video and then we'll work it out together. Ready to try? So in 3 seconds, our particle traveled 39 meters. I hope that this video gave you a fundamental understanding of the first fundamental theorem of calculus. Thanks for watching and happy studying.